Morning, everyone. Why don't we, still very early. Let's wait a bit till everybody comes in. Questions in the meantime? Morning, Abe. Mara, hello. Questions? How was the midterm? Too easy? I don't know when the final. Wait, the date for the final classes? Well, I mean, according to Minerva, I believe the last day is June 4th, but historically, the last 2 days were reserved for the final exam. So usually the final exam occurs on one of the last 2 days. So either June 3rd or June 4th is what I expect. So, which would mean that the last day for our class would be June 2nd. Let me just see what day that falls on. So June 2nd would be a Tuesday. That would probably be the last day of class. Unless something has changed that I'm not aware of, but I would assume that to be the case. So that means there's actually 2 weeks left. Exactly 2 weeks left. Questions in the meantime? Anybody? I don't know. I don't know when the final is going to be. The exam office is in charge of that. Historically, the exam was to be held on the last 2 days of class. So that would mean June 3rd and 4th, exactly that. Now, unless things have changed, because since we are allowing 72-hour final exams, will there be a rule that says it has to be finished by June 4th? Who knows? Probably not, since it really is just a 3-hour exam anyways, right? Just because you have 72 hours doesn't mean you'll need 72 hours. So all that being said, if it's the usual, it will either be June 3rd or 4th. The exam office is in charge of scheduling that, so we have to wait. Questions in the meantime? People are trickling in. How's everything going? Partial derivatives? Everybody comfortable with that? Should you have been able to do the midterm in 3 hours? For sure. Absolutely. In fact, should have been able to do it in probably less than 3 hours. It was actually a 2-hour midterm. 2 hours is what it should have taken you to do. No? How long did it take you? And let's have other people chime in as well. Because, you know, I mean, I was looking yesterday. Yesterday morning, I think most people had already submitted and never went back. Well, I mean, you had all 3 days. That was fine. Sasha is asking, should we expect the midterm to be the same length as the final? You should expect it to be longer, probably 50% longer. Yeah. Well, I mean, you had all 3 days, right? That's the thing with a 72-hour exam. You can use all 3 days, and why wouldn't you? And of course, you want to do everything you can to get 100%. Anything you legally can, right? So there's no reason for you not to use the 3 days. You know, you do a bit. You stop working on it, you keep thinking, and you go do other things. Enjoy the sun. The final is cumulative, absolutely. Questions? Anybody? It is 11. We'll start with the material. Unless there are questions. No, we're good to go. Yeah, Yushen is asking, in what case does the partial derivative not exist? Well, I mean, don't even ask for partial derivative, ask for the regular derivative. If you have a function, when does the regular derivative not exist? And if you take a function like x to the 2/3, the derivative, you get a 1 over. Well, 2/3, 1 over x to the 1/3. And that doesn't exist at 0. So the same thing happens with a partial derivative. You know, I mean, if you throw in a y there somewhere, then the partial derivative will not exist at x equal to 0. Partial derivative with respect to x. Amar is asking if I'll make the final considerably more difficult than the midterm. Well, look, I mean, by the nature of the final exam, since it is cumulative, it will be more difficult. There's really 2/3 more material, right? I mean, for the midterm, we had essentially just covered 1/3 of the material. So 2/3 of the material for the entire course is coming. So it'll be more difficult because there's more material. The questions themselves will not be more difficult. I hope to have everything marked by Friday. So midterm marks should come out on Friday. Tony is asking about the epsilon delta definition. Are we setting up delta or epsilon? Epsilon is given. You have no control over epsilon. The delta you have control over. You can choose the delta. And that's really the whole point of the epsilon delta definition, right? If epsilon greater than 0 is given, you have to show there exists a delta. So you have to choose what delta actually is. Valentina is asking when the final is. I don't know. The exam office is in charge of that. It's my understanding it should be June 3rd or 4th. Emily can find out the interval of convergence for number 2. I mean, what were you using? It was just a simple ratio test. Ratio test did the job. I will post a new web work probably today after class. Yishen is suggesting if we can say that we are finding a relationship between epsilon and delta. Yes, exactly that. No, Tony. Perhaps the TA misspoke. Delta is not given, right? In the definition, epsilon greater than 0 is given. Show there exists a delta. So you have to come up with the delta. Oh, Emily found the interval convergence, but could not find the value to which it converges to. It was not a trivial question. It was not a trivial question. This was the question. N squared x to the n, 0 or 1, whatever. Well, let's discuss it because I think it was a nice question. I don't know what you I don't know if you'll agree. Remove the n squared. You know what that is, right? You know what that is. This is the geometric series. This converges to that. If you differentiate the whole equation with respect to x, you know you can do that term by term interval of convergence. So here the derivative is n x to the n minus 1. And the derivative of this is that. So you see, you have n, you want n squared, but you're already a lot closer than you were. If this had been x to the n and you differentiate it again, you'd be where you want to be. So do exactly that. Multiply the whole equation by x. So you get n x to the n. And differentiate again. This will bring down the n again, and you'll get an n squared, x to the n minus 1. And the derivative of that, whatever that is, you're almost there. You're going to multiply the whole thing by x. Again, there it is. All right. Let's go back. Last time we introduced the idea of partial derivative. And from a graph perspective, what was going on? You had this function. And if you fix the point and look at its image, right, so this is f of AB, and if you imagine cutting your function parallel to the x-axis, right, you would get a nice curve. And we were asking, what is the derivative at that point? This was the partial derivative, right? So, I mean, we're bringing everything back to the one-dimensional case. And similarly, if you cut it in the y direction, we could ask the same thing. What is the derivative with respect to y? That's what the partial derivatives actually give you. So with this in mind, we can ask the question, what is the plane that contains both of these vectors? What is the plane that contains both of these partial derivatives as vectors? What is the tangent plane, right? As opposed to tangent line in the one-dimensional case, here in 2D, we ask for the plane containing both of these, so the tangent plane. Notice that all the points on this surface here can be described in this way, right? For every point xy, you go up a height of f of xy. So this describes every point on the surface. This tangent vector here, this vector in the direction of x, can be found by differentiating this vector here with respect to x. So if you differentiate each component with respect to x, with the assumption that x and y are independent variables, you get this tangent vector, if you will. Similarly, differentiating with respect to y yields this tangent vector over here. And if we want to describe the tangent plane, so we want the normal vector, which is perpendicular to each of these, you know what to do. We're just going to take the cross product. Minus fx minus fy and 1. This is the normal vector to the tangent plane. And that's it. While we're here, let me introduce the idea of a normal line, which is the line parallel to this normal vector going through that point. The normal line will have direction vector the same as the normal vector. Let's do a few examples from the book. Is the normal a plane? Well, this is the normal. So the normal vector. But we talk about the tangent plane, where the tangent plane is a plane that contains those two partial derivative tangents. Yeah, exactly. Let's take an example. Here we're asked to find the tangent plane and normal line to this function at this point. So I mean, if we define we can talk about fx, which is y squared e to the x. So fx at the point 0, 3, if x is 0, y is 3, we get 9. And fy, let's do it here. The derivative of this with respect to y, 2y e to the x. So fy at the point 0, 3 is 6. And the tangent plane has this as normal. So your tangent plane ax plus by plus cz equal to d, and now you just want to make sure that it goes through this point. So when x is 0, y is 3, that's minus 18, plus 9 is minus 9. In other words, this is your tangent plane. Yishen is asking, can the normal line pass through any point as long as it's parallel to the normal vector? Well, again, you want it to pass through this point. So here's your tangent plane, and then the normal line. Goes through that point, 0, 3, 9, plus t times the direction vector. So minus 19 minus 60 plus t. Let's try another one. So you know what we're looking for? dz dx, which is 1 over y squared, at the point minus 4, 2. This is 1/4. dz dy is minus 2x over y cubed. And at the point minus 4, 2. This is positive 1. And consequently, your tangent plane so minus 1/4 x minus y plus z is equal to d. And again, you wanted to go through that point. So 1 minus 2 is minus 1. Minus 1 is minus 2. In other words, 1/4 x minus y plus z is minus 2. This is the equation of your plane. Normal line going through that point. Minus 1/4 t minus t plus t. How are we doing? Questions here? Let's remember in Cal 1, right, when we introduced the idea of tangent line, we had this idea of tangent line approximation. For values close to A, your function is very close to the tangent line. So if x is close to A, for x close to A, f of x was close to this. This was known as linearization. Or tangent line approximation. Right? Meaning that f of x minus f of a over x minus a was approximately the derivative. So this was known as linearization or tangent line approximation. In higher dimensions, you have exactly the same idea. if you have this function, then at this point, the function is more or less equal to its tangent plane. Right? So your function is more or less can you see that? Y minus B over there? Terrible. Well, let me rewrite it again in case you cannot see it. What I'm suggesting is that f of xy is approximately equal to its tangent line. There we go. Let me point out, if I may, at this moment in time, that these two terms form the first two terms of the Taylor series. Right? These two are the first two terms of the Taylor series. We're going to see that we have the same thing happening here. We're going to extend Taylor series to higher dimensions. And these three terms here will be the first three terms in the Taylor series. So this is again known as linearization, or in this case, tangent plane approximation. Let's illustrate. We are asked to find the linearization of the function near the point how are we doing here? So Ahmad is asking if linear approximation was just Taylor series all along. Well, it was just the first two terms of the Taylor series. Exactly that. So here we go. point pi over 4, 2, what is that? Tangent of pi over 4 is 1, so this is just 2. Take the derivative with respect to x, which is y secant squared. And add the point pi over 4, 2, what is that? Secant of pi over 4 is root 2. So that's root 2 squared, which is 2, times 2 is 4. Fy is tangent. So Fy at pi over 4, 2 is 1. And so according to this, for values of xy close to pi over 4, 2, this is 2 plus derivative at 2 times x minus pi over 4 plus Fy times y minus 2. Let me put a 1 here for completeness. But there it is. Or if you prefer, 4x plus y minus pi. There you go. All right, moving on. Let's move on to the chain rule. And let's recall the chain rule in one variable. You from Cal 1, right? Math 140, you remember this. And you're very comfortable with this chain rule. Here, we'll have several variations of the chain rule, similar to this idea. Let's start with one observation. Consider the following scenario where you have a function of two variables x and y, where x and y are both functions of t. So imagine that occurring. Then your function z, right? I mean, if you replace both of these functions of t into this, your function z would itself be a function of t. Then z is a function of only one variable t, and consequently, the derivative of z with respect to t makes a lot of sense. And this is the regular derivative, right? Not the squiggly partial derivative. Your function is a function of just one variable t. So it's the ordinary derivative that we're talking about here. The derivative of z with respect to t, how would you take the derivative of z with respect to t? Both of these are functions of t. You want to differentiate everything that is a derivative of. You want to differentiate everywhere there is a t. And there's going to be a t in both of these variables. dz dt is df dx, partial derivative here, right? Because x is a function of t. So df dx, dx dt. But you've got the same thing happening in the y. df dy, dy dt. Let's illustrate. Consider this. You have two options. You could replace x and y with these things and then just differentiate with respect to t. Why don't we do that? All right, so that z really is just a function of t. So that if you differentiate dz dt, right, this is just a quotient, so quotient rule applies, and it's the usual derivative. V u prime minus uv prime. Can I write it here? Minus u v prime the whole thing all over v squared. Let's not waste any time simplifying that. All I want to point out is that it coincides exactly with what the chain rule tells you. Right? Chain rule tells you differentiate with respect to x times dx dt. So if you differentiate dz dx, this is the chain rule. So v u prime minus u v prime all over v squared. And dz dy is v prime minus u v prime all over v squared. So if you if we calculate this, so dz dt is dz dx dt, which is e to the pi t times pi, plus dz dy dt, and if you plug this in for that, and this in for that, and then replace x and y with what they actually are, well, it's going to be a lot of work, but it should give you exactly this. I'm going to let you finish that up, but that's what's going to happen. Well, maybe we should finish it up. Why don't we do that? Dx dt, dz dx is this. So replace. This is e to the pi t plus 2 e to the minus pi t minus all over and we're multiplying this by e to the pi t times pi. Let me leave this second part right as it is. Well, I think we'll understand sufficiently what's going on with this first part here. Let's convince ourselves. This part is exactly this. First of all, notice that the denominator is the same. So it's that times e to the pi t times pi, right? So this part times that we have right here. And then we will have this times that as well. And then from here, you'll get the other terms. You'll get this one and that one as well. In the chain rule formula, the usual d and the partial d can still be canceled. Well, it's a terrible abuse of notation, right? But think of canceling them to give you the idea, essentially. Instead of canceling them, what I like to think is that you're hitting everything where there's a t present. Yeah. Consider a second version of the chain rule. Suppose that z is once again a function of x and y, where x is itself a function of s and t, and y is another function of s and t. Then z is itself a function of s and t. So we can ask the question, what is the derivative with respect to s? What is the derivative with respect to t? And dz ds, well, z depends on x and y, but x and y both depend on s and t. So dz ds is df dx, dx ds, plus df dy, dy ds. Right, again, think of canceling these, and you're left with df ds, df ds, df ds. The idea is you want to differentiate everywhere there's an s, but there's an s in both x and y. And similarly, you can ask the question, what about dz dt? But that's df dt. That's df dx, dx dt, and df dy, dy dt. Quinn is asking, is dz ds the partial or the normal derivative? Somebody want to answer that? Is this a partial or is this the usual? Z is a function of both s and t, so it's the partial. As soon as you have more than one variable playing a role, it's the partial. Let us find dz ds and dz dt in two different ways. First, by just plugging in. X is s squared t, so x squared sine y becomes this, and you see that this is a function of s and t. This is s to the 4 t squared sine st. So it makes complete sense to ask, what is dz ds? And you know how to take the derivative of that. It's a product, so product rule applies. 4s cubed t squared sine st plus s to the 4 t squared cosine st times the derivative of the inside with respect to s. There it is. But now let's do it using the chain rule. Let's calculate dz dx, which is 2x sine y, and dz dy, which is x squared cos y. And we said dz ds is dz dx, dx ds, plus dz dy, dy ds. So this is that 2x sine y, dx ds, you can do that in your head. This is 2st, dz dy is x squared cos y, dy ds is just t, and if you replace x and y with what they are in terms of s and t, x is s squared t, y is st, x is s squared t, y is st, and that should be, well, let's clean that up. This is 4 s cubed t sine st plus s to the 4 t cubed cos st. First terms agree. S to the 4t cubed cos st, exactly the same as this. It's a valid question, right? Ahmad is asking, if the first method is easier and more intuitive, why bother with this second approach? Well, here, the functions were given. Everything was given, so you had options. What if you don't have options? Right here, everything was given. Very nice and easy. Do we want to do another example of something like this? Are we comfortable with that? Or do we want to see a harder example? Another example, let's do another one. Let's do another one where both options are available to us here. Let's calculate dz dt both ways to convince ourselves of the validity of the chain rule, right? If you plug in x and y, right? Here's your function, which is a function of both s and t. So we can ask the question, what is dz dt? Well, your function is an arctan, so the derivative is 1 over this squared plus 1 times the derivative of the inside with respect to t. So this is s squared. This is ln squared, so the derivative is 2 ln t times the derivative of the inside. Here the derivative of t squared is 2t. E to the 2s is kept as fixed. All right, now let's do it the other way. Right, so dz dt is dz dx dx dt plus dz dy dy dt. Let's work that out. Dz dx, derivative of arctan, is 1 over x squared plus y squared squared plus 1 times the derivative of the inside times the 2x times dx dt. Dx dt is s over t. Dz dy is 1 over x squared plus y squared all squared plus 1 times the derivative of the inside with respect to y, so times the 2y, times dy dt, which is just e to the s. So if you replace x and y with what these are, notice these are the same. Let's factor that out. This is 1 over s ln t squared plus t e to the s squared, this whole thing squared. And then we're left with this. So 2x, 2 s ln t times s over t plus 2y, 2t e to the s times e to the s. And this denominator is exactly what we have here. Here we have a 2s squared ln t over t, 2s squared ln t over t, and 2t e to the 2s, which is exactly what that will give us. How are we doing? Right? I mean, it's important important to understand what is happening. And let's look at the derivative here again. When you differentiate, you start by differentiating the tangent, so you get this piece here, which was present in both. And then here we're differentiating with respect to t, so you're going to differentiate this business, which was a square. So you get twice that. That's your 2x, right? Because this is really x squared. So you get your 2x, and then you differentiate the inside with respect to t, which is the s over ln t. I mean, s over t, right? The derivative of ln t is 1 over t. So you get an s over t, which is right here. And same when you do this part over here. Is everybody with us? Let's take an example where you don't have that option of doing it both ways now. Here it is. A very nice final exam question. Very nice, because Wolfram Alpha won't help you here. And if you don't know what to do, you don't even know how to begin. All right. Well, it's a train wheel question. Let's evaluate the UDS. U is a function of x and y. We don't know what function. We cannot make an assumption. We cannot take an example. U is some arbitrary function. It was probably assumed in the question that the partial derivative, the partial derivatives of U or the partial derivatives of f actually existed. Let's make that assumption as well. What is the UDS? Well, U is a function of x and y, where both x and y are functions of s and t. So dUdx is du dx dx ds plus du dy dy dx. Right? You want to differentiate everywhere there's an s. U is a function of x and y, but x and y themselves are functions of s and t. So there's an s in x, and there's an s in u, in both of these. du dx, we don't know what that is, right? Because u is just some function. So it is what it is. We don't know. Dx ds, though, we do know. That's e to the s cos t. Similarly here, du dy, we don't have enough information to work that out. But dy ds is e to the s sine t. Similarly, du dt is du dx dt plus du dy dt. And once again, we don't know what du dx is, but dx dt is negative e to the s sine t. And du dy we don't know, but dy dt is e to the s cos t. All right. So now let's evaluate this. So e to the minus 2s. If you square this, let's square that. This is du dx all squared. Right? I mean, I'm squaring this big thing. So it's that squared, e to the 2s cos squared. And then this times 2. Well, I'm going to quickly run out of room here. Let me write it here. So this is e to the minus 2s. What did we say? Du dx squared e to the 2s cos squared. And then we said this times 2. So du dx, du dy, 2 e to the 2s sine cos. And then we have this squared. Everybody with us here? That's just for this part. That's the du ds all squared. And then I'm going to add du dt all squared, so square this, and that is du dx squared, and this squared, which is e to the 2s sine squared, and then this times 2, so minus, right, because of this, du dx, du dy, 2 e to the 2s sine cos, and finally this squared, du dy all squared, e to the 2s cos squared. Beautiful. Hopefully some stuff cancels out. And this business cancels out with that one, because one is positive, the other one is negative. And then what? Let's get rid of this. Can we group some like terms? Here, this plus that, so e to the minus 2s, we can factor out a du dx all squared and e to the 2s, and we're left with sine squared plus cosine squared, which you know to be just 1. So that's du dx all squared e to the 2s, and then you get sine squared plus cosine squared, which is 1. And if we do the same, this plus that, again, sine squared plus cosine squared is 1, leaving you with du dy e to the 2s, du dy all squared, e to the 2s. Yishen wants to confirm that du dx all squared is not the same as d squared u by dx squared, right? Just to be clear, this is notation for the second derivative. This is the square of the first derivative. Completely different things. And I mean, you see that we're done now, right? When you multiply this into that, it's going to cancel, and you'll be left with du dx all squared plus du dy all squared, exactly what you wanted to prove. How are we doing? But speaking of the second derivative, let me bring your attention to an even nicer question with the same thing. And they're asking us to show the second derivative. So maybe I'll put this on the final instead. I'll let you work that out. Here, we are talking about the second derivative. Let me start you off, if I may. We had the first derivative, right? Du ds we had found, well, yeah, actually, I don't want to start you off. I'm going to let you work that out. No, let me start you off. Let me start you off. Where u was a function of x and y. X was e to the s cos t. And y was e to the s sine t. Is that correct? Is that what we had? Yes. Again, we won't do all of it, but I do want you to do it at home, and let me start you off on the right path. We had, right, so what are we looking for? We're looking for the second derivatives. So du ds was du dx, dx ds, plus du dy, dy ds, which was dx ds was e to the s cos t, and dy ds was e to the s sine t. Well, that's just the first derivative. You want the second. You know what you're going to do. You're going to differentiate this whole equation with respect to s. Again. And so here you'll get the second derivative of u with respect to s. So now you want to differentiate this whole thing with respect to s. Well, this doesn't depend on s, so that's just going to be a constant. You've got an s here, and u, which was originally a function of x and y, both of which depended on s, du dx is still a function of x and y. And x and y still depend on s and t. So you've got a product here. So differentiate this one, leaving that one fixed. So that's e to the st. That's e to the s cos t, leaving du dx fixed. But then you're going to leave that fixed. And you're going to differentiate this with respect to s. And that's where the confusion starts. What is that? What is the derivative with respect to s of du dx? It's just the chain rule again. This is a function of x and y. So the derivative with respect to s of this is the derivative with respect to x of that times dx ds plus the derivative with respect to y of that times dy ds. It's exactly the chain rule again. If you replace this with some function, big F, of x and y. The derivative with respect to s of this is the derivative of this with respect to x times dx ds, plus the derivative with respect to y of this times dy ds. That's exactly what the chain rule says. Well, here it's going to be the mixed partial derivative. Absolutely. d squared u by dy dx. So I'll let you finish that up, but there it is. U was originally a function of x and y. U was originally a function of x and y. So its derivative with respect to x, du dx, is still a function of x and y. So when you differentiate with respect to s, right, the chain rule kicks in. It's that same chain rule that you had here. Well, this ds dx, du dx, so d by ds of du dx, this is not a mixed partial derivative. Exactly. Right? Compare this with that. It's the same thing. If you replace this du dx with some function, df dx, dx ds, df dx, dx ds, plus df dy, dy ds. Anybody? Questions? Maybe we need to finish this question? Do we? Tell me now. Any questions? How are we doing? All right, let's do it. Let's do it from the beginning, because I will be running out of room if I try to do it this way. This is what we're trying to show. And we worked out du ds, which was du dx, dx ds, plus du dy, dy ds. And we had worked that out to be dx ds was e to the s cos t, and du dy, dy ds was e to the s sin t. That was not an issue. The issue arose when we tried to differentiate this whole thing with respect to s again. What is the derivative of that with respect to s? Or what is the derivative of this with respect to s? Well, let's just look at this first part. This doesn't depend on s, so that's just a constant. We have an s here, and here, what is that? Ask yourself this, what is this function? This is a function, u was originally a function of x and y. So the derivative of x, the derivative of u with respect to x, du dx, is still a function of x and y, where x and y are themselves functions of s and t. So the derivative of this with respect to s, you have to differentiate everywhere there's an s. There's an s in x, and there's an s in y. So when you differentiate this, d squared u by ds squared, the derivative of this, so first of all, it's a product, so you'll have a product rule. The derivative of this with respect to s is the derivative with respect to x times dx ds plus the derivative with respect to y times dy ds, leaving this part fixed. And then you leave that fixed, and you differentiate this with respect to s, and you get that. And same thing here. The derivative of this with respect to s is the derivative with respect to x, dx ds, plus the derivative with respect to y, dy ds, leaving e to the s sine t fixed, and then you leave du dy fixed, and you differentiate that. Product rule. Let's clean that up. D by dx is applied to du dy only, or du dx here. Yeah. So it's only applied to the first thing. Yeah. Maybe I should put some brackets here. But the next step will clear that up. So this is, let me change notations to make it simpler. This is uxx. And dx ds is e to the s cos t. And this is u xy. dy ds is e to the s sine t. The whole thing is being multiplied by e to the s cos t. And we have a ux e to the s cos t. And then we have a uyx dx ds is e to the s cos t. Here we have a uyy dy ds e to the s sine t. These two terms are being multiplied by e to the s sine t. And I've got a uy e to the s sine t. I don't need this last bracket here. There it is. So du dx is a function of both x and y, which is why we are using the product rule twice. Exactly that. Product rule, but also chain rule, right? Maybe it was the chain rule you were referring to here. Either way. All right. Similarly, du dt is du dx dx dt plus du dy dy dt. And if you differentiate this whole thing with respect to t once more, here you've got a product. So this is going to be, well, let's differentiate this one first. So that's negative e to the s cos t ux. And I'll leave this fixed, e to the s sine t. And I'm going to differentiate this with respect to t. And this is a function of both x and y, both of which depend on s and t. So that is du dx, dx dt, plus the derivative with respect to y times dy dt. And similarly here, I'm going to differentiate this with respect to t. So that is minus e to the s sine t, leaving uy fixed. And then e to the s cos t. And then I'm going to differentiate this with respect to t, which is a function of x and y. So it's uyx dx dt plus uyy times the derivative of y with respect to t. All right. All right. So what happens if you add these two things? So if you add those two things, let's leave the e to the negative 2s outside. What happens if you add these two terms? First of all, do things cancel out? We're not expecting mixed partial derivatives, so hopefully they'll cancel out. Here you have a uyx, and here you have a uyx. Let's look at the coefficient. Es cos, so E cos times E sine, so two of the E's and a sine cos. Two of the E's, sine cos, but here it's negative. So this is going to cancel out with this. Similarly, uxy, here you have E squared sine cos. Here you have E squared sine cos, but it's negative. So again, these cancel out. We don't have first partial derivatives, so that should cancel out. I've got a ux e cos minus ux e cos. So these cancel out. Uy e sine minus uy e sine. These cancel out. What does that leave me with? I've got uxx e squared cos squared plus uxx e squared sine squared. So uxx e squared cos squared plus uxx e squared sine squared. You see what's going to happen, right? And uyy e squared sine squared and uyy e squared cos squared. So these two combine to give you uxx e squared plus uyy e squared, because the sine squared plus cosine squared is 1. So that's e to the minus 2s, uxx e to the 2s, uyy e to the 2s, and when you multiply that in, you just get uxx plus uyy, exactly what you wanted to show. It's a bit haphazard on the board there because you kind of run out of room. But on paper, it's much easier to see. How are we doing? Questions here? I'll give you a minute to copy that down. Everybody with us? It's a nice final exam question. It's not that complicated if you know what you're doing. If you don't know what you're doing, it shows immediately. All right, let's get rid of that. Top right corner, yes. What happened in the last part again? Top right corner. When you combine these two terms together, factor out a uxx, e to the 2x, you're left with cosine squared plus sine squared, which is just 1. Same when you combine these two terms. You get a sine squared plus cosine squared, which is just 1 again. So that's why you're left with this, and then multiply it out. The exponentials disappear, leaving you with uxx plus uyy, exactly what you wanted to prove. All right. Let's move on by coming back to what we were looking at, right? I mean, we discussed the partial derivative with respect to x and y. And we understood that when you're taking the partial derivative, you're really measuring the rate of change of the function. Quinn is asking if this works for third and fourth derivative. Well, I mean, the chain rule extends naturally to however many functions you want, right? I mean, we only did it in 2 here. I mean, I guess we probably should have mentioned it in 3 and higher dimensions, but yes, everything extends immediately to higher dimensions. And let me just write down a chain rule argument, if you will. If you have a function w as a function of x, y, and z, and if x is a function of s and t, y is another function of s and t, and z is yet a third function of s and t, then w itself is a function of s and t. And we can ask the question, what is dw ds? Well, w is a function of x, y, and z, where x, y, and z are themselves functions of s and t. So you've got an s in each of these variables. dw ds is dw dx, dx ds, plus dw dy, dy ds, plus dw dz, dz ds. And so on and so on. So chain rule extends to however many variables you're dealing with. Let's go back to this partial derivative business, right? We saw how the partial derivative of f with respect to x really measures the rate of change in the x direction here. And similarly, df dy measures the rate of change in the y direction. But now if you think back to continuity, we saw that in 3 space, or in the xy plane, there's more than just 2 ways to get to a point, right? There's more than just the x direction or the y. You could come to any other direction you want. So in the case of the derivative, it makes sense to ask, what is the rate of change in some other direction? How does the function change if you were to cut it using another plane? What would happen then? And this is the idea behind directional derivatives. Why limit yourself to just the x direction or the y direction? Why not discuss other directions? Other directions given by some direction u, a unit vector. Let u be a unit vector. We define the directional derivative of f of xy in the direction of u denoted by duf to be the limit as h goes to 0 of f of x plus ah, y plus bh minus f of xy all over h. Observe, if you will, if the unit vector AB is the vector 1, 0, so if B is 0 and A is 1, what do you get? Quinn is asking, U is not the equation? What do you mean? U is some unit vector AB. I'm saying, in particular, if you take the unit vector 1, 0, you get the partial derivative of f with respect to x. Exactly that. And if you take the unit vector 0, 1, of course, you see what you're going to get. You get the partial derivative of f with respect to y. So you see that this directional derivative business is really an extension of the partial derivative, right? The partial derivative is really a special case if you take good unit vectors. Ahmad is asking if we can evaluate it without the definition. Well, indeed, we'll get to that right now. But I just wanted to point out that the directional derivative was in fact an extension of the idea of partial derivative. And now let's try to evaluate this limit. What is that limit? So right, let's rewrite this. Let's look at this limit for a moment. And what is that limit? If you plug in what happens if you plug in, Yishen is asking, can AB be 0, 0? We are assuming AB to be a unit vector here. The 0 vector is not a unit vector. So we want to stay away from that. We are restricting our attention to unit vectors. Right? And in order to give us a direction in which we want to go, a direction in which we want to measure the rate of change. If you're not moving anywhere, there's nothing to measure. As h goes to 0, what is happening here? If you replace h with 0, both of these are gone. And the numerator is f of xy minus f of xy, which is just 0. And the denominator is 0 as well. So this has the form 0 over 0. Makes a lot of sense to use L'Hopital's rule here. We're going to differentiate with respect to h. Is u in the xy plane? It is. U is in the xy plane. So it's the direction in which we want to go. Of course, this extends to higher dimensions. So this has the form 0 over 0. We're going to use L'Hopital's rule, differentiating with respect to h. And what is the derivative with respect to h? Well, there's an h in both the first component and in the second. This does not depend on h at all, so the derivative is going to be 0 here. And if you differentiate with respect to h, what do you get? There's an h in the first component, and there's an h in the second component. So chain rule kicks in. And the derivative is the derivative with respect to the first component times the derivative of the inside. Plus the derivative with respect to the second component times the derivative of the inside. The whole thing divided by the derivative of the denominator, which is 1. And as h goes to 0, this goes to 0, this goes to 0, and we're left with f1 times a plus f2 times b, which can be put together, if you will. Does the first component here mean the entire x plus ah? It does, but f1 really means the derivative with respect to the first component. So if you had called this s, it would have been fs. Absolutely. Which we can rewrite as f1, f2 dotted with the original unit vector u. So this is f1, f2 dotted with u. Which leads us to define this business definition given a function f of xy. We define the gradient of f, denoted gradient of f, or del f, to be df dx, df dy, or, this extends to higher dimensions, or df dx, df dy, df dz, if you were in 3D, or more if you were in higher dimensions. This gradient idea extends to as many dimensions as you want. So the question is, find the gradient the rate of change of f and the rate of change at the point P in the direction of the vector V, where the function is this, the point P is the point 1, 2, and the vector is the vector 3, 5. So somebody's asking, what is the direction, what is the relationship between the directional derivative and the gradient? What is the relationship between the directional derivative and the gradient? I just rubbed it off here, but the last line gave us the answer. So let's repeat it here. If U is a unit vector, we just saw that the directional derivative of f in the direction of u was actually the gradient of f dotted with u. That's the relationship between the two. As we'll see in this example here, first let's work out the gradient of f. The gradient of f is df dx, df dy. So you know what to do. The derivative here, partial derivative with respect to x, it's a quotient, so quotient rule applies. V u prime minus u v prime over v squared. And the partial derivative with respect to y, that's a bit easier. Minus 2xy over x squared plus y squared all squared. So gradient at the point 1, 2, let's work that out. That's 4 minus 1, which is 3, over 4, 5, 25, and minus 4 over 25. Everybody with us here as far as the gradient is concerned? So that's the gradient at the point P. And now we want the rate of change at the point P in the direction of V. In other words, we want the directional derivative. But directional derivative is only defined for unit vectors. So we're going to change V into a unit vector. How do we do that? Right, we want to go in the direction of V. When it's asking graphically what is the gradient, let's hold off on that. Let's hold off on that momentarily, and I'll come back to that in a few minutes. Let's first ask exactly, right? We're going to divide by the magnitude. Your vector V, we're going to divide V by its magnitude to get a unit vector in the same direction as V. So that is 3/5 divided by 25/34. Is that right? 34? Root 34? And consequently, the directional derivative at the 0.12, or the rate of change, is just this dotted with that. So 9 minus 20 is minus 11 over 25 root 34. There it is. So Poon was asking, graphically, what does the gradient represent? And since we've observed this, let's use that to determine what is really going on with the gradient here. The directional derivative we just saw was the gradient dotted with u. Now, if you think back to 133, you know the dot product is length of one vector, length of the other, times cosine of the angle between the two. So, let's ask this question. Well, first of all, you know what's going on with the cosine business, right? You know that cosine is always between -1 and 1. So this is always less than or equal to that. And in fact, it's maximized. This maximum is achieved when cosine is equal to 1, or when theta is equal to 0. So the maximum occurs when theta is equal to 0, or when u is in the direction of the gradient. So this directional derivative, which is the rate of change of the function in the direction of u, this is maximized when u is in the direction of the gradient. The rate of change of f in the direction of u is maximized. Maximized when u is in the direction of the gradient. And it's minimized right? The smallest this gets is when cosine is -1. So when theta is pi, or when u is in the opposite direction of the gradient. So let's bring this back to a graphical interpretation of what's happening. The gradient gives you the direction in which f increases most rapidly. Right? If you're here and, imagine locally what your function looks like. I mean, suppose that it's increasing most rapidly in this direction, that's going to be what the gradient is. It gives you the direction in which your function increases most rapidly. And negative of the gradient is the direction in which it decreases most rapidly. So that's graphically what is happening with the gradient. Let's take another example. Same question as before. We are asked to find the gradient and find the rate of change of the function at the point P in the direction of V. Same question as before. Here, however, we have a function of 3 variables. So the gradient, you know what it is. Partial of f with respect to x. So df dx, df dy, df dz. Or in this case, y squared r10. Partial derivative with respect to y is 2xy r10. And partial derivative with respect to z there it is. The gradient at the point 2, 1, 1 is what? Arctan of 1 is pi over 4. So that is pi over 4. 4 times pi over 4, which is just pi. And lastly, 2 over 2, which is 1. The gradient is a vector, absolutely. And again, graphically, it gives us the direction in which the function increases most rapidly. Amar is asking if we're only going to do up to 3 variables. No. Everything extends to as many variables as you want it. So it's all good. right? I mean, if you can do 3 variables, you can do 4 and 5 and as many as you want. So in most cases, there's no point in going higher than 3, but it's always possible to do so. So that's the gradient. We're going to change V into a unit vector. By dividing by the length, and consequently the rate of change of f in the direction of u, or the directional derivative, is just the dot product of these two vectors. So pi over 4 root 3 plus pi over root 3 plus 1 over root 3. There it is. How are we doing here? Questions? So we saw these two nice properties of the gradient. Namely, that it gives you the direction of most rapid increase, and negative of the gradient gives you direction of fastest descent, fastest decrease. Let's observe one more nice observation. Suppose that you had some function in 3 space, and let's describe it most generally. Suppose you had an implicit function. Where z could perhaps be implicitly defined as a function of x and y. Right? Maybe you're not able to solve for it, but whatever. If we look at level curves, where a level curve is a one-dimensional object, so you could describe it using one variable only. So you have x, y, and z, possibly, depending on some variable t. Let's differentiate the whole equation with respect to t. You've got a t in both the first, second, and third components. So the derivative is going to be f1 times the derivative of the inside, plus f2 times the derivative of the inside, plus f3 times the derivative of the inside. The derivative of a constant k is 0. And this left-hand side can really be rewritten as f1 F2, F3, dotted with dx dt, dy dt, dz dt. T is a parameter here, absolutely. This is a bit out of context because the book describes curves in some chapter that we skip. I'm going to come back to it at the end of the course, and we're going to do a whole development of curves at that time. So this is a bit out of context, but let's just go with it. All I want to do is point out an important characteristic of the gradient. And what do I want to point out? I want to point out that this is, in fact, the gradient of this function. And what this last equation is saying is that the gradient is orthogonal to this vector. And what is this vector? Well, it's a vector made up of the derivatives as the components. So it's not a big stretch to understand this as the tangent vector. And what we're suggesting is that the gradient is orthogonal to the tangent vector. So the gradient is normal to the level curve here. Right? If you have this curve, this is going to be your tangent vector, and we're saying that the gradient is orthogonal to the tangent. So the gradient is normal to the level curve. And this extends. So the gradient is normal to the level curves. Or level surfaces. Surfaces. So let's put all of that together. Before we do that, let me point out in particular, let's bring this back to a situation that you already saw. If you have z as a function of x and y, we saw that the normal vector, the vector normal to the tangent plane, was the vector minus fx minus fy 1. Bring the f of x, y to the other side. This is really z minus f of x, y equal to 0. This is a level curve, or in this case, a level surface, where this is your new function big F. what is the gradient of this? The gradient of this function, right? It's a level surface because it's equal to a constant. The gradient of this, what is that? Well, partial derivative with respect to x, so negative fx. Partial derivative with respect to y, negative fy. Partial derivative with respect to z, positive 1. Exactly that. Isn't that nice? Let's put everything together in a nice, concise theorem that governs everything we have now understood about the gradient. Theorem. Let f be a differentiable function of 2 or more variables, and the gradient of f at some point x naught is not 0. If u is a unit vector, the directional derivative of f in the direction of u at the point x0 is the gradient dotted with u. The gradient of f at the point x0 points in the direction of greatest increase. Of f at the point x0. And that maximum rate of change what is the maximum rate of change? We did not point that out. Right, the maximum rate of change was going to be this, dotted with the unit vector corresponding to that. So that divided by the length which is really the absolute value of the gradient. Right? It's the length squared divided by the length, so the absolute value. So the maximum rate of change is this. Similarly, the fastest rate of decrease is in the direction of the negative gradient, and that rate is negative of the absolute value. Negative of the length. Greatest increase, yeah. And finally, the gradient is orthogonal well, in fact, let me say the gradient is normal to level curves or surfaces of F through. Excellent. Maybe a good place to end for today. We'll pick this up again tomorrow. And we'll do a few examples of this. See what's going on. Questions in the meantime? Thank you all for coming. Any questions? Anybody? No, we're good? So practice this. I'm going to open up right now a web work. Yeah, I'm going to go do that right now. So I'll see you all tomorrow. Thank you. Pretty sure 263 is not going to be offered in a second session. Usually most math courses are offered in May. Then they offer a Cal 1 later on, but it's really an exception. Yeah, so there's not going to be anything else offered. I'm quite certain of that. Thank you very much. I'll see you guys tomorrow.